Bismillahirrahmanirrahim. Today the topic on which we are going to discuss is Theorem 14.1.3. The internal bisector of an angle of a triangle divides the sides opposite to it in the ratio of the lengths of the sides containing the angle. Theorem 14.1.3. It's given in triangle ABC. Internal angle bisector of angle A meets CB at the point D. On the other words, if we discuss this statement with detail, then first of all we have to know about angle bisector. Array which divides any angle into two parts is called angle bisector. In this triangle ABC, when array AD divides angle A into two congruent angles, angle CAD and angle BAD are measure angle 1 equal to measure angle 3, then this ray AD is called interior angle bisector of angle A of triangle ABC. Measure BD ratio measure DC is equal to measure AB ratio measure AC. We have to prove measure BD ratio measure DC equal to measure AB ratio measure AC. In triangle ABC, when angle bisector AD divided into two congruent angles, angle CAD and BAD, at that time opposite side BC is also divided into two parts BD and ratio DC. This divided side is equal to the ratio of the length of the sides containing the interior angle A. So measure BD ratio measure DC is equal to measure AB ratio measure AC. Draw line segment BE parallel DA to meet CA produced at point E. Draw line segment BE parallel DA to meet CA produced at point E so that triangle ABC and triangle ABE are formed. A line segment AD parallel to one side EB of triangle EBC, which divides the other two sides BC and EC proportionally. By using theorem 14.1.1, a line parallel to one side of a triangle divides the other two sides proportionally. In the triangle ABC, when measure AD parallel to measure EB, then measure BD ratio measure DC is equal to measure EA ratio measure AC, where AD parallel EB is also its construction. First of all, we have to discuss equation 1, which is measure angle 1 is equal to measure angle 2. It is a corresponding angle. When two parallel line segment AD parallel EB are intersected by a transversal line segment C at point A and E, then four pairs of corresponding angles, alternate angles and vertical opposite angles are formed. But in this triangle EBC, only one pair of corresponding angle, measure angle 1 is equal to measure angle 2, lie in this triangle EBC, which is equation 1 of the proof. Secondly, we have to discuss on the alternate angles. Measure angle 3 is equal to measure angle 4. When two parallel line segments AD parallel EB are intersected by a transversal line segment AB at point A and B, where AB is an other transversal line segment in the triangle ABC, then four pairs of corresponding angles, alternate angles, and vertical opposite angles are formed. But in this triangle ABC, only one pair of alternate angles, measure angle 3 is equal to measure angle 4, lie in this triangle, which is equation 2 of the proof. Now we have to discuss on equation 3. Measure angle 1 is equal to measure angle 3, which is given. We have already discussed on it when angle A is divided by array AD, then two congruent angles are formed. Angle CAD congruent angle BAD or measure angle 1 is equal to measure angle 3. Here we have to discuss on equation 4, measure angle 2 is equal to measure angle 4. From equation 1, measure angle 1 is equal to measure angle 2, and equation 2, measure angle 3 is equal to measure angle 4. Then given equation measure angle 1 is equal to measure angle 3 becomes measure angle 2 is equal to measure angle 4, which is its equation number 4 of the proof. In triangle ABE, two angles, angle 2 and angle 4 are congruent. Then opposite sides AB congruent AE are also formed by using theorem 10.1.2. In a triangle, the side opposite to the congruent angles are also congruent. This statement can also be written in another form. If two angles of a triangle are congruent, then the sides opposite to them are also congruent. In this triangle, if angle 2 congruent angle 4, then it's proof side AB congruent side AE, which can also be written in this form. Measure side AB is equal to measure side AE, which is equation 5 of this proof. Here we discuss measure AD parallel measure EB, which is equation 3. By using theorem 14.1.1, in a triangle EBC, a line segment AD which is parallel to the side EB divides the other two sides BC and EC proportionally. Mean when measure AD parallel to the measure EB, then measure BD ratio measure DC is equal to measure EA ratio measure AC, which is also written in this form. Measure BD over measure DC is equal to measure EA over measure AC. So when AD parallel EB, then measure BD over measure DC is equal to measure EA over measure AC, which is equation 6. Here we discuss on its proof. Measure BD ratio measure DC is equal to measure AB ratio measure AC. From equation 5, measure AB is equal to measure A, and equation 6, measure BD over measure DC is equal to measure EA over measure AD. The equation measure BD over measure DC is equal to measure AB over measure AC is formed. It can also be written as measure BD ratio measure DC is equal to measure AB ratio measure AC, which is its proof of this theorem.